Uh, First of all, have a great afternoon to everyone. It's a greetings from Bulgaria. Currently, I'm also in a summer school at Bulgaria in my network. So yeah, great. Today I'm gonna talk about the new generation imaging spectrometers from AVIRIS, NG, and HyPlant. And I personally feel these two airborne spectrometers are very new, and new in the sense like the protocols they develop for Earth observation. It's amazing. I mean, it's very new in Earth observation system. It will solve so many wide problems in spectrometric calibration, validation to different applications of Earth observation. So yeah, here I will start about some talk about AVIRIS NG, and also I will start with the HyPlant imaging spectrometer. Yeah, so today I'm gonna lecture on AVIRIS NG and HyPlant, and I divide my lectures in two parts. First part, I will talk about the general information about AVIRIS NG, and then I'll come to an application that I'm currently working on with AVIRIS NG for future space missions. And in a second part, I will talk about HyPlant airborne imaging spectrometer, and I am also going to talk about another application using HyPlant for spectrometric observation using sun-induced fluorescence signals for its estimation and modeling. Yeah, so as we all know about AVIRIS, NG is quite famous. In those who are working with imaging spectroscopy, they are quite familiar about the airborne spectrometer AVIRIS. So it has been developed by NASA, and so it basically covers the visible infrared and imaging part of the electromagnetic spectrum. And so AVIRIS have two parts. There is also the older version is called the AVIRIS Classic, and the new generation is the AVIRIS NG. So the purpose of developing AVIRIS is to provide a high signal to noise ratio imaging spectroscopy measurements. So with the more less noises, with the high spectral to noise ratios, and particularly in the solar reflected spectral range. And it is expected to be replaced the AVIRIS Classic one, which is the previous version of AVIRIS, which is since flying in 1986. So this picture is very new. It's just in 2 months back. There is a massive airborne campaign of AVIRIS NG from JPL, NASA, and University of Zurich. And I was there also for visiting at Swiss Military Air Base. So yeah. So the basic specification of AVIRIS NG is to the wavelength that covers mostly 380 nanometer to 2510 nanometer, with a spectral resolution of 5 nanometer to 0.5 nanometer, moving in around this, with a field of view of 36 degree to with 600 resolved elements. Yeah, it's quite good in all aspects of spectrometric parameterizations, and it is right now having great demand for those who are working with the imaging spectroscopy for different Earth observation purposes and these stuffs. So you can also get the data sets from AVIRIS NG data portal. It's 2014 to till date. They are very active to uploading the new data sets. It is mainly controlled by the JPL NASA, and here you will get both the radiance data and the reflectance data, and it's fully free of cost. I mean, it's open access data sets. So here you can see some of the flight scenes that I have taken. This is the ocean water. There are some parts of the snow and vegetation and sand. So the thing is like the main problem is this imaging spectrometer, that it doesn't have any global coverage. There is some particular aerial flight lines, and if you are interested in the flight lines, and it's sometimes if it matches with your study area, you can surely get the data set from AVIRIS data portal. It's completely free. So here you can see this red patches are the flight lines showing It's mostly covered in the US. Nowadays, it's covered parts of Europe, almost mostly the western part of Europe, and also some measurement have been done in India and some parts in the northern Canada. Yeah, but for those who are working with the high altitude Earth observation science, so for them there is also imaging data sets are available at the Greenland. So yeah, now I will move in a particular specific application of AVIRIS NG airborne spectrometry for reference scene generation for a future space mission, which I'm currently working on at University of Zurich. Yeah, so the mission target is for the TRUTHS. TRUTHS is a operational climate focused satellite mission, which will be in space in 2028. So with the main aims to quantify the estimation of the climate change drivers, mostly the radiation, albedo, aerosol optical depth, even some vegetation indices and other parameters to provide more highly accurate and trusted climate records in SI units. So this is the future mission for 2028, mainly controlled by European Space Agency and UK Space Agency. So our job is to particularly develop the reference scenes for the future space mission using AVIRIS NG spectrometry data to make this approach more repeatable and traceable. And finally, this is going to be used for end-to-end simulation. Those who working with sensor simulation or future space mission related work, they should know about this end-to-end simulations. So our end, we have to generate the reference scenes using different models, particularly in radiative transfer modeling approach, to provide the reference scenes for further simulations. So here we mostly collected the airborne hyperspectral data. Again, this is mostly based on the available campaigns. And we try to use both AVIRIS NG and APEX. APEX is our self-developed imaging spectrometer from University of Zurich. And but we are mostly working with the AVIRIS dataset because of the distribution of the data in different parts of the world. So we collected data from the Greenland, from the US, North America. We have some datasets from also India, from Europe. So our target is basically to cover the all kind of natural features from snow area, forest area, it's lake, desert, ice covered plates, in everything. So basically we are deriving the reflectance product from these particular areas. Yeah, so here is a full processing chain of the AVIRIS NG data product. So to obtain the final reference scenes for the TRUTHS mission. At the first, you can see at the bottom of atmosphere reflectance, we are receiving the very first level data of reflectance data sets, level L2 products. Then we subset it with 640 across track pixels with 425 bands. And then we have done the resampling of the imagery with 1000 by 1000 pixels. Then with some specific method, we do the spectral upscaling. And then we also have developed the TRUTHS virtual sensor, which is the future space mission sensor. And we further simulated these reflectance cubes with the sensor to get the final product. Now, with the final product, we have also verified the accuracy of the final product. So on the other hand, from the reflectance space data set directly from the AVIRIS NG sensor, and we plotted the radiances obtained from there, and also calibrated radiances obtained from the final product. So we also cross-validated them, and it was a bit done mostly in the ATCOR. ATCOR is a radiative transfer modeling based simulator. And here we have some spectral resampling response file generated in a specific MATLAB codes. And further, we also provide the virtual sensor characterization in this particular simulator to simulate the scene for the purpose of the future satellite properties. And then finally we obtain the results, and you can see like we have a very good correlation between the original data of AVIRIS NG and further simulated truth sensor radiances. So yeah, this is a result from a Railroad Valley sandy area in US, but we have received a good correlation between the original data and simulated calibrated data. With the almost you can see the radiance curves are almost fitting to each other very well, and the same methodology we have used for the other landscape, also for the forest area, for the snow area, and for the lake areas. So yeah. And because it was also the need from the ESA that we have to simulate the images for further solar zenith angles. So here is some example that we simulated the images for different solar zenith angles at the 10 degree, 30 degree, and 60 degree. And these are the spectral responses from different solar zenith angles. And also you can see in the forest areas. So at 10, 30, and 60 degree observations. Yeah. So now I come to the another imaging spectrometer, which is HyPlant. HyPlant is also a very newly developed imaging spectrometer. It has been developed in around 2012 or 13. I don't know the exact year, but this is the one of the newest airborne spectrometer for that particularly developed for fluorescence measurements. So it's a very high performing aircraft that have the spectrometer for measuring the sun-induced reflected fluorescence and also the reflectances. And the most important thing is that this sensor is the airborne demonstrator of ESA Sentinel-3 Flex Fluoris satellite, and have been developed jointly by Fortune Center Munich and Spacium Imaging Limited private company in Finland. Yeah, so here I will present one data set from the HyPlant imaging spectrometer, but before that, I would like to focus on the like the system of the HyPlant airborne spectrometer. So HyPlant spectrometer constellated with two different modules, flow module and dual module. So the flow module is mostly based on the 670 to 780 nanometer spectral range, with a very high spatial resolution of 0.25 nanometer, and that particularly developed for the fluorescence mapping. And on the other hand, there is dual module, which is mainly operated between 370 to 2500 nanometer, with the spectral range between 3 to 10 nanometer. This is mostly capturing the reflectances and to useful for the derivation of the different vegetation indices. So here I'm going to present a data set from 11th of July 2015. There is a summer school, swamp summer school in Poland, and which is mainly organized by ESA, UFR, and Flex mission framework. And I have done my PhD work also in these data sets. Yeah. So this is the main study area, the experimental site of my work. This is the whole Jetchin peatland area. And we have also a team of botanists, those who are always working with the botanical distribution of this area. So you can see we have different kind of composition of ecosystems like peatland, grassland, and forest areas. And the central part is mostly is the peatland area, is a swamp area. So it's always a challenge for those who knows about the peatland surface spectroscopy. It's really a challenge because of the distribution of different species, composition of different species and plants within a small area, and huge spectral diversity. So it's not so easy to disentangle the signals from this such a complex surface. So, yeah, so we mostly covering the peatland area. I have also worked with the grassland, which is mostly located in the edges of the peatland. And the other part, rest of the parts are mostly covered by the forest areas, mostly the pine forest areas in this area. Yeah, so from I have not went to the more processing of the data set, but it is the final product that from you can see that here I have calculated that all the vegetation indices from simple ratio to NDVI, EVI, PRI. So these have been derived from the HyPlant dual module based spectrometer, and on the other hand, which have a more higher specific spectral resolution to capture the sun-induced fluorescence at 760 oxygen absorption band A at the far right position, and on the other hand, I have also calculated the CIF 687, which is also called the oxygen absorption band B at red fluorescence. So basically, we have used the spectral fitting method for deriving the fluorescence from the radiances. And here you can see also the simple formulas that we have been used for calculating the vegetation indices of different parts, from simple ratio, which is and NDVI, which is mostly covering the greenness part. The biomass have been covered by the EVI, and chlorophyll concentrations with NDVI RE and zenithophil cycles have been covered mostly by PRI index. So yeah. So I'm going to present a small modeling work in using this airborne spectroscopy datasets. So here is a full schema of the methodology that I have been adopted for the whole modeling chain. You can see that from airborne spectrometer, we have two different modules, dual module and flow module. So from the dual module, we derive these different vegetation indices from simple ratio to PRI. And on the other hand, using the SFM method, we have the sun-induced fluorescence map at oxygen absorption band A and B together. So then we have used the fuzzy simulator to, this is a two-step simulation process. First step is to doing the membership function to derive the membership maps of different variables. And on the other hand, in the next stage, these membership functions have been collaborated together to process the final map. Here we are using fuzzy gamma function, and finally receive the CIF fuzzy, which we termed as CIF fuzzy. And then we furthermore, on the other hand, we also calculated the PAR NDVI, and from PAR and NDVI we calculate the APAR and injected the APAR signals to the CIF fuzzy to get the CIF fuzzy APAR. And now these are my modeled data. On the other hand, we have also the original spectral measurements and original sun-induced fluorescence map. And furthermore, we validated the model with the original images, and to try to check out that does this model work perfectly for this thing or not. So yeah, and we also scaled the works up to the ecosystem level, and covering the different ecosystems from forest, grassland, and peatland areas. So here is small discussion about the fuzzy simulator. Fuzzy is a kind of a approach that allows to for more flexible combinations of the weighted maps, and that could be readily implemented using the spatial modeling technique. So it is I can connect these things with our human observations, like with the expertise at the data sets and rule set, we finalize with the crisp data to move to the fuzzy sets, and then finally the defuzzification process to get the final outputs. So this is a kind of a weighted average mapping of the simulators, and to get the final outputs. This is the whole processing chain of the data set. So here you can see the different vegetation indices. So with the different membership functions, we received the different membership maps of variables. And finally, we combined all the membership maps into the fuzzy gamma simulator to get the CIF fuzzy, and then we further injected the APAR signal into the CIF fuzzy to get the CIF fuzzy APAR. This is the, now I come to the outputs. So this is the derived membership maps of the area, which is covering the no membership to still high membership of 1. We have tested with different combinations. It is very simple, like to combine with different combinations, like from combination 1, we are considering all the vegetation indices, and also from the combination 2, only 3. At combination 3, we have only 2, at 4, at 2. So with different combinations. So as you know, like different vegetation indices are reflecting the vegetation treats. So we try to optimize this model with the combination of different treats to find out which particular combinations is giving us the best fitted method to in reference to the original SIP signals. Here is the SIP fuzzy maps which you derived at 6 different combinations, and it is the validation of the combination based. So here you can see we have the original SIP maps at both oxygen absorption bands, and we have also the model data. So we compared with the first combinations. We found that the high correlationship with 0.62, also with the simple ratio and PRI also giving the good correlation at for 760 SIF. And on the other hand, for 687, like the combination 1 is giving the highest correlation, and simply the last one, the simple ratio and PRI also giving the high correlation at the R square of 0.90. This is the after injecting the APAR signal into the SIP fuzzy. So this is the SIP fuzzy APAR outputs at different 6 combinations, same as like before, but this is after the injecting the APAR signal into the SIP fuzzy map. And here we see that the original SIP maps and the model SIP map, the correlation have been more improved in compared to previous one. So here we can see the changes in the combinations have provide you more good, better accuracies that after injecting the APAR into the SIP fuzzy and the final of SIP fuzzy APAR, it's giving a more better estimations at in response to the original data sets. So yeah, so you can see this the R square have been improved to 0.75. It reach up to the 0.80. And for but there is no such big change have been observed for 687. It more or less it's constant with the previous one. So but it have been greatly improved for 760 at far red fluorescence. Yeah, I hope that's all for my side. If you have any question, please feel free to ask.